So far, we've seen how DC circuits operate. We've solved circuits with resistors, capacitors, and inductors. Now, we will take these circuit elements and apply them to alternating current circuits as well. Let's start by reviewing the behavior of an AC generator. A generator contains an armature that rotates within a magnet. The frequency of the generator measures how many cycles the armature makes per second. It is measured in a unit called Hertz. 1 Hertz means 1 complete cycle per second. As the armature rotates, it produces an alternating voltage. We call this graph a sine wave or a sinusoidal wave. A sine wave has 2 parameters that are relevant to us. One is amplitude. The amplitude of a sine wave is a measure of its height. It is measured as half the distance from the peak to the trough. In this diagram, we see that the top sine wave has an amplitude of 1 unit, while the bottom sine wave has an amplitude of 2 units. Two sine waves that have the same amplitude and frequency can still be different if their peaks are not aligned. In this case, we say that the 2 waves are out of phase. For instance, if the 2 waves are identical, but one reaches its peak when the other wave reaches its zero, we say that the waves are 90 degrees out of phase, or that the phase angle is 90 degrees. If the peaks do match up, we say the waves are in phase, or the phase angle is 0 degrees. Different phase angles are possible if the peaks are closer together or further apart. In this example, we see that the phase angle is 30 degrees. Remember when we were working with DC circuits with resistors, we were introduced to Ohm's law, V equals IR. The current in a circuit depends on the voltage of the battery and the overall resistance in the circuit. We can rewrite this equation as V over I equals R, that is, voltage over current equals resistance. The reason we will do this for this video is that it will provide a new way of understanding resistance. Resistance is the ratio of battery voltage to current in the circuit. Another way to think of this is, if you have a certain voltage, the resistance provides the proportion that tells you what the current will be. The resistance controls the current. So, for instance, if you know that the battery voltage is 5 volts and the current is 0.5 amps, that means the resistance must be 5 volts over 0.5 amps equals 10 ohms. That's the proportion. Now, let's apply this logic to an AC circuit. The biggest difference between an AC circuit and a DC circuit is that in an AC circuit, the voltage is now variable. In fact, the voltage regularly cycles between positive and negative values. Suppose we used an ammeter to measure the current at different times. We would get a graph that looks like the graph at bottom. We see that it's a sinusoidal graph. In fact, the graph for current has a different amplitude than the voltage graph, but it has the same period and is in phase with the voltage. So we can say the phase angle is 0 degrees for any AC circuit that contains just a resistor. Just like in the DC circuit, the voltage and current are in proportion to each other. If we just compare the amplitudes, the maximum voltage and the maximum current, we could say that Vmax over Imax equals R. Now, let's build an AC circuit with a capacitor instead. To keep things simple, we will assume the circuit contains a generator and a capacitor. What happens to the current once it has stabilized? Remember that in a DC circuit, as a capacitor charges up, it hinders the flow of current and the current slows down. Something similar happens here. As the generator's voltage increases, charge builds up on the capacitor and the current drops. When the generator is at maximum voltage, the current is 0. And that's not all. When the generator voltage starts dropping, the capacitor starts discharging. As the capacitor discharges, the current reverses direction. In fact, the current keeps moving in the opposite direction until the other plate of the capacitor is completely charged, and then the cycle starts all over again. Over several cycles, we can see that when the current is at its peak, the voltage is zero. We say the current and voltage are 90 degrees out of phase. And since the current always reaches its peak before the voltage, we can be even more specific by saying 90 degrees out of phase, current leading, voltage lagging. We also observe that the amplitude of the voltage sine wave is different from the amplitude of the current sine wave. Like before, we can set up a ratio of Vmax to Imax, but unlike before, the ratio is not equal to R, obviously because there's no resistor in the circuit. Instead, we call this ratio the capacitive reactance. It is symbolized with the Greek letter chi sub c. The Greek letter chi looks a bit like an X. It is calculated by this formula, 1 over 2 pi times the frequency of the AC source times the capacitance of the capacitor. This equation says the bigger the capacitance, the bigger the maximum current. This makes sense. A bigger capacitance means that more electrons can be stored on a capacitor to produce the same voltage, while a smaller capacitance would mean fewer electrons are needed to max out the capacitor voltage, and that would make the capacitor more restrictive. The equation also says the bigger the frequency, the bigger the maximum current. This also makes sense because the more quickly the AC generator reverses the direction of the voltage, the less time there is for electrons to gather on the capacitor plates. Next, we'll build an AC circuit with just an inductor. Remember, an inductor prevents quick changes in currents and turns them into gentle changes instead. Here is the equation for an inductor. Basically what it says is, when the current is constant, the voltage is zero. More specifically, if the voltage is falling through zero, the current is at its maximum. And if the voltage is rising through zero, the current is at its minimum. Long story short, once the system stabilizes, we get a pattern like this. The current always reaches its peak or trough when the voltage is zero, and vice versa. Also, the current always reaches its peak after the voltage does. So we would say the two waves are 90 degrees out of phase with voltage leading and current lagging. What about the amplitudes? Well, the ratio of the amplitudes, Vmax over Imax, is given by a term called the inductive reactance, which is symbolized by chi sub L. It is equal to 2 pi times frequency of the AC source times the inductance of the inductor. Basically what this says is, if the inductance increases, the inductor will be better able to restrict the current. And if the frequency of the generator goes up, the inductor, which prevents quick changes in current, will again restrict the current more. You're probably wondering what would happen if all three types of circuit elements, resistors, capacitors, and inductors, were in the same circuit. How would we relate the current and voltage then? It's instructive to note that the capacitor and the inductor have exactly opposite effects. The capacitor makes current lead voltage by 90 degrees, and the inductor makes current lag voltage by 90 degrees. With both present, the current might lead or lag, but by less than 90 degrees. In other words, it will not reach its peak at the same time that voltage is zero. To characterize the relationship between voltage and current, we first need to calculate the capacitive reactance, chi sub C, and the inductive reactance, chi sub L. The equation for phase angle is as follows. Take the arctangent of chi sub L minus chi sub C over R. A positive value means that voltage is leading. A negative value means current is leading. The ratio of the amplitudes is called impedance and is symbolized with the letter Z. Impedance equals the square root of resistance squared plus chi sub L minus chi sub C whole squared. Let's see an example. Suppose you have a 1 volt AC generator operating at a frequency of 0.5 Hz, meaning the armature makes one complete cycle every 2 seconds. The circuit also contains a 0.5 ohm resistor, a 0.1 farad capacitor, and a 2 Henry inductor. The capacitive reactance is calculated as shown. We work it out to be 0.314 ohms. The inductive reactance can also be calculated. It is equal to 0.159 ohms. We can put these values into the phase angle equation to find out that the phase angle is negative 17.22 degrees. We can also put it into the equation for impedance, and we find that the impedance is 0.523 ohms. What this means is if you were to graph the voltage and the current, they would both be sine waves, but the current would reach its peak slightly before the voltage, not a full 90 degrees, but only 17.22 degrees, as shown in the comparison between these two graphs. We would also see that the current is actually quite a lot larger than the voltage. This is the result of the impedance, the ratio of voltage over current, being less than 1. As a parting thought, there is a condition for AC-RLC circuits called resonance. In resonance, the effect of the capacitor and the inductor cancel each other out, and the current returns to being in phase with the voltage. For this to happen, you have to change the frequency so that the capacitive reactance and the inductive reactance are the same. This equation shows you the resonant frequency of any AC circuit. So for the circuit that we had designed with a 0.1 farad capacitor and a 2 Henry inductor, the resonant frequency is 2.81 Hz. At this frequency, the current will be in phase with the voltage. This video covered virtually everything you need to know about AC circuits. You should now be able to determine the amplitude ratio and phase angle for a circuit with a resistor, a capacitor, or an inductor, or all three. And in the latter case, you should be able to determine the resonant frequency of the circuit.